Hello everyone. Today we're going to talk about the addition of floating point numbers in hardware level. We will start with concrete examples, so let's begin. But before we start seeing examples about the addition, let's answer this question, which is very important. It says here how the floating point number addition and subtraction operations are determined to be executed by computer. The short answer is it's up to the compiler. The compiler determines if this is going to be addition operation or subtraction operation. Okay, let's answer and see some explanation. Okay, first of all, since the arithmetic operations are binary operations, then we need three registers actually. These two of them will store the operands. We can call them R1, R2, and the third register R3, which will store the result of the operation. Let's see this example. In a high-level language, if we ask to perform this operation, saying 3.47 plus 6.23, it's direct, clear operation, which is going to be addition. Okay, and in here we will store the value 3.47 as a positive floating point number in R1, register 1. We're going to store 6.23 in R2. Then we will make the addition and store the result in R3. Thus, in here, it's clear that we have addition operation. In assembly language, the format, I'm talking about the MIPS assembly language, for as a reference, we're going to say add R3, R2, R1, meaning add the value stored in R1 and add it to the value stored in R2 and then store the result of the addition in R3. It's direct, simple, and clear. Another example, this one. In here, is this gonna be addition operation or subtraction operation? Okay, if we check this one, it says like this. This is the same as 6.23 minus 3.47. Okay, that's make big difference. And here for the first look, we think this is gonna be addition operation by adding the minus 3.47 adding to the positive 6.23. Actually it's not. It's gonna be subtraction operation. We will subtract 3.47 from 6.23. And this is how it's gonna be. First we will store the value, the positive value of 3.47 in R1. Then we will store the positive value of 6.23 in register 2. And then we will make the subtraction and store the result in R3. Thus, in here we have subtraction operation. And in assembly code, it's going to be look like this. It's going to be sub R3, R1, R2. Notice here we change the order of registers according to the order of numbers in here. And in here it means that you will subtract gonna be R2 minus R1 and the result will be stored in R2. As you can see, this is R2, this is R1. We're subtracting R1 from R2 and then store the result in R3. So in this case we have subtraction operation. In here it's not addition. Who determined this? The compiler. Okay, we'll move to the next example. In this example, as you can see, we see here minus 3.47 minus 6.3. Okay, is this addition or is this subtraction? In here it's addition. We are adding the negative value of 3.47 with the negative value of 6.3. This is how the compiler will translate it. So in here we're gonna store the minus value, the negative value of 3.47 in R1, and then we store the negative value of 6.23 in R2. Then we make the addition in here and store the result in R3. So in here we have addition operation. In assembly language, it's going to look like this: add R3, R2, R1. It's the same as adding R1 with the R2 and then store the value in R3. But in this case, the values stored in R1 and R2 are negative values, as you see in here. Okay, so in this case we have, this is addition operation. And final example here, if we make like this minus 3.47 minus 6.3, what is this? Is this subtraction? Is this addition? And this is the same as saying minus 3.47 plus 6.3, which is the same as 6.23 minus 3.47. So it's clear, it's become like this one, and this is going to be subtraction operation. So in this case, we are not storing the negative value of 3.47. We're storing the positive value in R1, and we store the positive value of 6.3 in R2, and we're gonna make subtraction operation. So this is gonna be subtraction operation, and in assembly language gonna be sub R3, R1, R2, and as you can see, this is meaning R2 minus R1, and the result will be stored in R3. So these examples are very important to make us understand what kind of operation it's gonna be, because this affect the addition and subtraction in a floating point number in terms of the logic circuit, because it's a common logic circuit. The logic circuit we're going to look at in hardware, it make the floating point number addition, and at the same time it make the floating point number subtraction. So we have to determine what's going to be. It's going to be addition or it's going to be subtraction, because the process of subtraction is more complex than the addition in terms of floating point number operation. That's why we have, first of all, it have to be very clear which operation we are going to perform. Okay, now let's step forward and start with example number 1. Okay, we start with this example. This is obvious example of addition of two floating point number. First of all, this is the initial step that we have to convert these numbers, which are in decimal form, into binary form that follow the IEEE 754 format. And I assume you already know how to do this, by how to convert these floating point number into their binary format, this format which will be exactly stored in memory. Okay, the IEEE 754 format has three parts. The first part is the mantissa, which is 23-bit, and the second part, the exponent, 8 bits, and the final part, which is 1 bit, the sign bit. This is the format that will be stored in memory. We do this for the first number and the second number. Okay, now the total is 32-bit. Okay, we go with the next step, which is step 1. This is straightforward step by extracting the exponent and the mantissa. As you can see, for the first number, we put its mantissa right here and then its exponent right here. And now we put the implied one or the leading one by putting dot 1. Very straightforward, very simple step. The same thing we do for the second number, as you see. Now we are ready to go to step 2. In step 2, we have to determine the difference between the exponent, and we do that by make the subtractions. So when we subtract the smaller one from the larger one, this is the smaller in this case, we will subtract this one from this one, and the result will be 1010, and this is kind of big number, it's 10 in decimal. Now this number telling us this is the shift amounts needed for this mantissa to be right shifted, so we can increase the value of this exponent so it can be equal to this exponent, and this is the whole target of this step. So after we made the subtraction and determined how many bits we must shift, in this case it's gonna be 10. So we perform that by shifting 10. Shifting is straightforward process. Of course, we are making here right shift. Right shift, you see this dot right here. We move one place, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we put the dot and then we put the leading 0. And in between we put the zeros after this one. So it's gonna be like this one. So as you can see, now when we shift the 10 bits, you see this one right here, this one goes right here, and then we move, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we put the dot and then the leading 0 become here, and this is how the shifting done. In this case we shifted 10 bits. Now since we shifted 10 bits, that we have to add the 10 to its exponent. So when we add to it, it become 1, 0, 0, 1, 0, 0, which is the same number as the same exponent, the same value of the other exponent. Okay, one more thing here to be look at is when we make the shifting and we increase the value of x exponent as a result of right shifting, we have some leftover bits. In this case gonna be 10 bits will be left over, which are 1 1 1 1 1 1 and 1 0 0 0. These called leftover bits, but we will only focus on the most significant 3 bits of them, which we're gonna call them the GRS. The GRS. Okay. Why are these bits are important? Now, before I move forward, in here we put 0 0 0. Why? Because this one has no leftover, and it says here. Let's read it up. And shift right the mantissa bits by shift amount from step 2 to make it exponent equal to the larger one. This is clear. We already done that. And we keep the 3 most significant bits of the leftover bits. We're going to call them GRS. If no leftover, then the GRS equals 0, 0, 0, triple zeros, as in this case. Okay? Now, what are the GRS? First, G stands for guard bit, R stands for round bit, S stands for sticky bit. The GR and S are simply the next 3 bits after the least significant bit of the mantissa. They are used mainly for rounding, which we're going to see by the end of this example. In this case, there is something wrong in here. Okay, in this case, they are the G equal 1, the R equal 1, and the S equal 1. Not like this. I have typo here. Okay. We move forward now. Step 4. Step 4 asking us to add. After we make the alignment, now both exponents are the same. Now we are ready to make the addition operation. When we add them, okay, first of all, we added the 3 bits, which are the GRS of this exponent and the GRS of this exponent, which are going to be the same because these are 0. It's going to be 1, 1, 1, which we're going to use later for rounding. Now, when we perform the addition, the result, the final result will be 0 plus 0, going to be 0, 0 plus 1, 1, 1 plus 1, 0, and then carry 1, 1 goes here, etc. And this is going to be the final result. Okay. Now, after we finish the addition, we're going to go for the normalization. What normalization mean? In normalization, we're going to look at the dot right here. If the dot is next to the leading one, then we are done. No need for any normalization. If not, then we have to make either left or right, depend on where is the closest leading one going to be. So, let's read this one, and it says normalize the final result if needed. Along with the GRS bits, this is important, we're going to see this in another example, either by shifting right and incrementing the exponent, as in this case, when we shifted right, we incremented the exponent, or shifting left and decrementing the exponent. We're going to see this in much more detail in other examples. In this case, we do not have any normalization because the point here is next to the leading one. So we are all set. Okay, now this value we ignore it, and in this case, and we now ready to go to the rounding step. Rounding has rules. Rounding, we round by adding 1 to mantissa. In two cases, if the GRS, we talked about the GRS before, if the 1 x here means don't care gonna be 0 or 1. So if G and R equal 1 and 1, then we have to make rounding by adding 1 to the mantissa. The second case, if the G equal 1 and R equals 0 and the sticky bit equal 1, in this case we have to make the rounding by adding 1 to the mantissa. Now the third state, or it says here, if the GRS equal 1 0 0, then we round the mantissa to the nearest even. We do not add 1 to the mantissa. It's big difference. We're gonna see this in much more details in another example. And finally, it says here renormalize. We have to make normalization again if the rounding generates carry. And this is special case. If all of these values are 1, when we add 1 to these all 1, then we have carry. In this case, we have to make another normalization. Okay. So let's see in this case, do we have rounding? Yes, because the GR equal 1 1 or GRS equal 1 1 1. We have to make rounding. How do we make the rounding? We add 1 to the mantissa, as you see. So when you add 1 to the mantissa, and this is the final result. As you see, of course, there is no renormalization, because when you added the 1 right here, it did not affect the whole mantissa. It just affect three bits, I guess, like this, or 2 bits, in fact. Okay. This is the final step. We're wrapping up the final result by putting this mantissa right here in mantissa part, and then the exponent in here, and then we put the sign of the final result, which is in this case 0. But how did we get it 0? Because both of them are zeros. They are not negative, they are positive number. So the final result gonna be positive. Okay, notice here the point 1 we ignored it, we discarded when we get to the final result. See, in this step 1 we already, and the final step we remove it. So we put it here, then we remove it here. But you know, using or putting the implied one is mandatory because we need it in the process. And this is gonna be the final result. If you like, as we did here, we converted into its hexadecimal, and as you can see, the addition of a floating point number in hardware level gonna generate this number, and it's gonna be stored in hexadecimal format or in binary format as in IEEE format. I hope this example is clear and the steps are clear, and I see you in example 2.